All right, this is Mr. Jern, and I'm going to explain AP Physics Workbook 5I, Momentum Representations. So we start with a scenario in which a ball is thrown up into the air with an initial speed of v naught. And then, after a few seconds, it returns to the height from which it was thrown. Air resistance is negligible. We're just going to ignore it. So it says to, in part A, sketch the following graphs as a function of time for the time the ball is in the air. Now, because we've been doing a lot of graphs, diagrams that look like bar graphs in a lot of ways, I just want to clarify that when they say sketch graphs as a function of something, that's typically, I can't think of a situation where it wouldn't be, going to be a scatter plot, a line graph, something like you're seeing right here. Okay, so that's your clue. So for position versus time, this is a ball that goes up into the air. So its position will go in the positive direction. Typically, unless there's otherwise a reason not to, we indicate positive as being up or up as being positive direction. And then it comes back down toward the negative direction. It is still in the positive. As it's up in the air, as it's coming down, it's still in the positive position, but it is losing that position, so to speak, and coming back down to where it started from. So it'll start at position of 0, and it'll end at position of 0. It will never go below the position of 0. It's always going to be above the position of 0. And keep in mind, this represents a ball that goes straight up and down. It is not following an arc. Our brains kind of like look at this and kind of imagine that the ball is following an arc. It is not. This is just as time goes on, the ball goes up and then comes down. Okay, so get used to reading these graphs again by saying the words that's representing. The ball goes up and then it comes back down. The ball increases its position and then its position decreases from there back to where it started from. The velocity time graph, we've seen these before, of course, where when you throw the ball upward, it has its maximum positive velocity, and then it immediately starts to lose that velocity because gravity's slowing it down. Then it gets to the halfway point, which should, on your graph, match the halfway point here. So it gives you grids for a reason. Use the grids and refer to the grids. These blocks, then the halfway point, should start coming back down, and this is the point where the velocity has reached 0, and then the velocity becomes negative because now it is falling downward. Okay, so if we agree up is positive, then down is negative, and so you have to represent that with your graph. Again, it'll come back down at the same speed that it went up with initially. So 1, 2, 3, 4, 5 blocks in this key was used to represent the initial positive velocity. So you should have 1, 2, 3, 4, 5 blocks to represent the negative velocity just before it lands back in the thrower's hand. The reason it comes down at the same exact time is because air resistance is negligible. So there's no air resistance doing work, slowing the whole thing down. Acceleration, it's due to gravity, and so this is represented as a constant negative downward acceleration. Close to what you might call 10. Again, there's no numbers on here, but as long as it's positive, as long as it's not positive, as long as it's negative and it is constant, you're good. For the potential energy, again, this is not going to be a fill in the boxes chart that we've been working with. It is a function graph. And so the potential energy of the ball earth system, potential energy is due to the, let's say, difference in position between the earth and the ball, also known as the height of the ball. And so as the ball goes up, the distance between them, the height, the delta y, will increase until it gets to the very top, again matching the same exact point, and then the distance between them will decrease again. Same thing for the time versus momentum. Since momentum is mass times velocity, then and the mass of the ball doesn't change. You can represent that with a graph that looks very similar to the velocity versus time graph. And since the net external force on the ball is all due to gravity, the force of gravity is going to be mass times the gravity of the ball. The Fg is equal to mg. And since m, again, the mass of the ball is going to be remaining constant, the g, the pull of gravity, will be 9.8 or 10 negative downward. And so it is going to look exactly like the acceleration on the ball. The total mechanical energy of the ball-earth system, since there is no air resistance doing work, removing energy from the system, then the total mechanical energy will stay the same. It will be either kinetic or potential. And this graph sort of it has to match, not match, but it has to go along with the next graph, the kinetic energy of the ball. You can see the total mechanical energy is drawn at this line here, and therefore this kinetic energy has to start at that same exact height, that same exact energy, because the ball starts with 100% kinetic energy. As it goes up, 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 it loses kinetic energy, and so the kinetic energy goes down. It's at a curve because of the squared relationship, and at the very top of the rise, the ball has stopped. It is 100% potential energy, which is not represented in this graph, and then it comes back down, mirroring the energy as it went up. The second page is all a bunch of statements. There's not really much to explain here. This is just how it is. This is just showing the representation. This is showing a list, essentially, of the relationships between constants and different variables and ideas. So my suggestion would be to go through this list, make sure that you got them correct, make sure you understand each one of them, and that is basically it. There's not much more to this one.